Hello and welcome back. So today I want to start working on a guitar effect, or effect pedal, or guitar pedal, or effect unit, whatever it's called. I don't know, I don't play an instrument. But the point is, these are quite interesting circuits from an electronic point of view, and other than that, you can build them actually quite well. So they're not that complicated and you can build it quite comparable in quality to a commercial unit. And other than that, what makes this sort of circuit really interesting is that it's actually a useful circuit. So it's something that you can use on a daily basis or however often you play your instrument. And to make things a bit more interesting, I plan on building a modular device. And what I mean by that is that I want to make more than one of these effect units, but to keep the effort and the number of components as small as possible. So if you're curious, then keep watching. So what goes into one of these effect pedals? Well, you can find a bunch of old schematics on the internet, so from various manufacturers, and other than the components mainly being obsolete, the principles by which these circuits work haven't really changed over the years. I mean, the basic operation for the analog effect is the same today as it was 40 years ago. Now, speaking of operating principles, what actually goes into an effect circuit? Well, again, by looking over multiple schematics, I will leave some links in the description just so you can look around. I came up with this block diagram. So, in an effect pedal, so in an effect circuit, other than the actual effect itself, so the part of the circuit that does some sort of sound conditioning, there's quite a lot of other things going on. So you will need to connect your effect circuit to the rest of the world. So you'll need input and output connections. And now, to not be influenced by any sort of external factors, like variation of impedances and so on, these connections are not directly connected to the effect, but in a good circuit, there's some sort of input and output buffer. So something that isolates the circuits in between themselves to keep things as linear and as predictable as possible. So you will be needing some sort of buffer circuitry. Now, of course, the effect is not a static circuit, so you don't want to have it as is and that's it. Usually there's some sort of knobs and switches and so on, something to fine-tune exactly how the circuit is affecting the sound that's going through. So normally you'll be having a bunch of potentiometers connected to it. And now, of course, any circuit needs to be supplied. So you'll need either a battery or a DC adapter, you'll need some sort of reverse voltage protection, some sort of filtering, power conditioning. Maybe you have a half voltage point, so some sort of voltage reference towards which you have a positive and a negative supply. Of course, you'll need some sort of switch to be able to activate and deactivate your circuit. And finally, since we're talking about effect pedals, you need the pedal itself. So you need a switch that is capable of activating and deactivating your effect circuit. So other than simply removing the supply of the circuit, one of the features that's commonly used in this sort of effect units is a way to have the signal pass through the effect or to bypass it. And now you can do this with a simple mechanical switch, but the downside of that is that you can mostly use this in between playing sessions. So when you will be activating or deactivating the bypass circuitry, usually there will be some sort of interruption heard in the sound. And that's not something you want. So what I want to do is have my pedal switch and use that to run some sort of electronic switch that creates a smooth transition between the affected signal and the bypass signal. And to get this thing to work right, I'll be needing my mechanical pedal switch, I'll be needing a divide by 2 circuit, so you'll need a circuit that will activate on the first push of the pedal and then deactivate on the second push, and then this circuit will be driving my 2 electronic switches that select which way the signal passes through the circuit. And the thing is, regardless of what sort of effect you're trying to build, everything except the effect itself will always be needed. So it doesn't matter what the effect is, if you want to build a proper circuit, you will be needing all of this peripheral stuff. So my plan is to build the circuit in a modular way. So first of all, I build all of this peripheral stuff, which includes most of the most expensive components, so connectors and switches and the casing and so on, and then have the effect added on top like a secondary board. That way you can build multiple effects and then just switch the boards. This way you will be using the least amount of effort to build as many effects as you want. So let's look at the circuit in a bit more detail. So let's start things off by looking at the digital part of the circuit. So the pedal switch and the divide by 2 circuit. So this is basically the circuit that we need. So we have our switch. I'm using a voltage source just to switch it to see how it works. It has a pull-up resistor, and then this is going into a flip-flop. In this case I'm simulating with a D flip-flop, which is performing the divide by 2 action. And if we run this thing, we see our input signal on the lower screen. So this is the signal coming into the clock input of the D flip-flop. And then on the upper screen, we're seeing the output. And this is exactly what we want. The output is switching every time the button is being pushed. So the first time the output is turning on, second time it's turning off, and so on. Now of course, since we're using a mechanical switch, its switching action isn't this clean, so it doesn't have a perfectly turn on, turn off cycle. With most mechanical switches, you have a bouncing effect. So when the switch is turning on, it doesn't directly turn on, it might jump a bit, there might be a bit of oxide, so it might not make contact the first time. And to simulate this, I made this PVL source that doesn't switch on the first time, there's a bit of bouncing in between. And if we look at how this behaves, we see that our input signal has this extra bouncing going on, and if we look at the output, well, we see it switching every time the input signal is switching. Because the flip-flop is counting not just our intentional turn on and turn offs, but it's also counting the bouncing effects. So what we need to do is remove the bouncing. And that of course is done with a debouncing circuit. Now it's a fancy name, but it usually implies just using a single capacitor. So what I got here is the same circuit as before, but I added this extra capacitor. And basically what this is doing is slowing down the way in which the signal coming from the switch is getting to the flip-flop. So instead of having a very sharp turn on, now we have this very slow turn on. And the slope of the signal is dictated by the value of the resistor and the capacitor. So now if we look at the output of the flip-flop, again it's working correctly. So it's dividing the input signal by 2. Now until now I've been using the default D flip-flop model that is found in LTspice. But if I move to a real component model, so what I got here is the model for the Texas Instruments 74 LVC 74 Dual D flip-flop, and this component has 2 problems. So first of all, the 74 series usually can handle a voltage of maximum 5.5 volts, and we will be using 9 volts because 9 volt batteries are common. I mean, we could take the 9 volts and make 5 out of them, but that's going to be complicated. But the second issue, which is a bit more important, is that this circuit doesn't really work. So if we look at what happens here, we see our input signal with the slope, so the debouncing is working. But if we look at the output, well, it's not switching correctly. So it's not dividing the signal by 2. And the problem is that the D flip-flop relies on a feedback between the output and the input D pin. And as long as your signals are quite fast and they have sharp turn-ons, this will work just fine. But with this sort of very, very slow input signal, the flip-flop doesn't act as expected anymore. And I know I tried this out a few years ago and it didn't really work in practice, so I'm fairly confident that the simulation is telling me the right thing. So what can we do? Well, the D flip-flop won't really work, but there are other flip-flops out there. And what we need is a T flip-flop. Now you can't get T flip-flops that easily, but what you can get is the JK flip-flop. And by interconnecting the J and the K pins, you get a T flip-flop. So what I got here is the same circuit as before, but this time it's done with the CD4027 dual JK flip-flop, which is a CMOS circuit, so it can handle up to 18 volts, so we can supply it at 9, no problem. We have our input filtration system, and now if we look at how the circuit works, so we see our input signal is filtered, everything is fine, and if we look at the output, we see that finally we're getting the response that we are wanting to get. So we have our divide by 2 behavior. Now there's just one more thing to mention about this part of the circuit, and that is regarding the switch. So we can see that the input signal is switching on very nicely, very slowly. There's no high currents involved, but the switching off effect is very abrupt and very sharp. This is mainly because the switch is directly short-circuiting the capacitor. And since there's no resistances involved, the current's a bit high. So in the simulator we're getting 70 amps going through the switch. And that's not a good thing. I mean, in real life it will be a bit lower because of the ESR of the capacitor and wiring resistance and so on, but it's usually a good idea to add some sort of current limitation so you don't destroy your switch. So the final thing to add into the circuit is this extra 100 ohm resistor in series with the switch. So if we look at the circuit behavior, it still behaves as expected. So we have our input slow turn on, we have the circuit dividing by 2 as we want it to. But if we look at the current going through the switch, instead of the 70 amps we had before, we only have around 80 milliamps. So this way there's no danger of destroying the switch. And that about covers the digital part of the circuit. Let's move on to the analog circuitry. So there's quite a bit to cover, so let's get right into this. So what I got here is first of all the power supply part. So I'll be using a 9 volt supply, and to get the half voltage point, so some sort of reference voltage that is at half the supply voltage, you can either use a simple voltage divider with a couple of resistors, or you can use this sort of op-amp circuit. So what I got here is a high value resistor divider, so this will keep current consumption low, and then I'm relying on an op-amp to take this voltage and repeat it, so this is configured as a voltage repeater, and this is going into a capacitor buffer from which I have a reference voltage that my circuit is connected to. And I added this extra 1 ohm resistor. It can have different values. The main purpose of this is to keep the circuit stable. Op-amps don't really like this sort of voltage repeater connection, especially if you connect them to a large capacitive load. It can lead to instability and oscillation. By adding the resistor you can prevent this. Now with the circuit itself, so I'll be using an input sine wave, and first of all I have an isolation, so a DC blocking capacitor, and this feeds into my input buffer, again configured as a voltage repeater. We have a bit of stuff we'll cover in a moment, and then on the output, again we have a voltage repeater, the output buffer, which coupled through another capacitor is going outside the circuit. Now inside the circuit, we have our affected path. So just to keep things simple, the effect that I'm simulating today is just a divide by 10 resistor divider. So just so we have two signals between which we can switch. And then we have our non-affected path on the bottom trace. Now I removed the flip-flops and replaced them with pulse sources just to keep things simple. And these are driving my analog switches. Now I built the switch with a JFET transistor. So this is not a bipolar transistor or a Mosfet, it's a JFET, junction field effect transistor. And what makes this sort of transistor special is that, first of all, it's a field effect transistor, so its operating principle relies on creating a conductive channel through which currents can go both ways, so that's why we need field effect transistor rather than a bipolar transistor. But secondly, unlike the Mosfet, the JFET has a much smoother transition between on and off stages. So it's far more linear, and in this particular case, that's something we need. So if we look at how the circuit works, well, it's simulating quite slowly. Main reason for this long period is that other than just looking at waveforms, what I included into this simulation is also these wave commands. So I covered this in an older video. Basically, you can set LTspice to save any sort of waveforms as a wave file so you can listen to them afterwards. So I'll be leaving a link to that video in the description. But the point is, we can look at this circuit, not just at the waveforms, but also listen to the switching action. And what I want to do is compare the JFET switches to the exact same circuit built with Mosfet switches. It's just gonna take a while. So finally, simulation is done. We have our input sine wave referenced around 0 volts. This goes in through the first capacitor, and then it gets referenced around the half supply voltage 4.5 so that it can be processed by the input buffer. Output of the buffer is exactly the same thing as we had before it. And then if we look at our switches part, so you can see that we have our switches alternating, so every 100 milliseconds, just to keep simulation time short. And if we look at the output, well, it doesn't look that pretty. So we can see that the switches are alternatingly passing through signal, First of all, the unaffected signal, which is this green signal. Now it's going up and down a bit, but that's just because of the capacitors. And then it's either letting this through or the affected signal, which is this much smaller signal. And finally we can see that the output signal is buffered by the output buffer, and then after passing through the capacitive isolator, it's again centered around 0 volts. So now coming back to why we were using JFET transistors, if we look at the signal that combines the affected and the unaffected ones, and we zoom in a bit, we see that the signal is transitioning from one to the other quite smoothly. So we see that our affected signal is slowly being combined with the unaffected one, and then only the unaffected signal is being left behind. On the other hand, if we look at the same thing with the Mosfet circuitry, so here we have the exact same input-output signals, everything is the same, it's just the transistors that are different. And if we look at the transition here, well, it's inverted because of the way the transistors work. So we're going from the unaffected signal to the affected signal, but the transition is extremely sharp. So we see that the transition is this glitch, really, that happens in between the two signals. So basically the main advantage of using the JFETs as analog switches is the smooth transitioning between one signal and the other. So by using that sort of transistor, you can keep playing and then just switch in between the affected and unaffected sounds without causing any sort of audio discomfort. Speaking of audio discomfort, let's quickly listen to how the two sounds actually sound. So first of all, if we listen to the JFET sound, we see that there's a quite soft transition between the two signals. On the other hand, if we turn to the Mosfet sound, we see that there's a much sharper transition and a much more obvious transition. Or maybe it's just me. And this is the final schematic that I came up with. So let's start off by looking at the power supply section. Now normally you would need some diodes to select between the battery and the DC adapter, and you would also need a switch to turn the device off. But in this case I'm relying on the connectors themselves to help me out on this. So a normal connector for a DC adapter, other than the two pins for the ground and the supply, also has a third pin, which is connected to the second pin, but when something gets plugged into this connector, then this connection disappears. Basically, by using this, I'm connecting the battery to my positive pin through the DC adapter. But this only happens when there's nothing plugged into the adapter. Once something gets plugged in, the battery gets disconnected, and I'm using the DC adapter to supply the circuit. Now, to get the supply to turn off, so to not waste any power when the device is not used, I'm relying on the input jack. Now, most FX circuits work with mono signals. So you'll be using this sort of mono jack that just has a single line of signal and a ground pin. Now, this is different from the stereo type of jack, where you also have this second channel through which you have the stereo sound. Now, when you plug a mono jack into a stereo jack connector, your second channel will get short-circuited to ground by the mono jack. And that's exactly what we're using here. So my third pin, which would be the second channel, will get short-circuited to ground when the jack is plugged in. And this is what I'll be using as my turn-on switch. So this device will only get supplied when there's a jack plugged into the input connector. Now afterwards, I added the two options for the circuit that can supply our half voltage point, so either a resistor divider or the op-amp solution. I have my digital circuitry, so built around the JK flip-flop. We got our FX switch connector, we got the debouncing circuitry, the flip-flop itself. I also have some LEDs, one to show me that I'm having an affected signal going through the circuit, and one to show me that the device is supplied. Then we have our analog circuitry, we have our input and output buffers, and then the two JFET switches, which are connected to the digital side. And finally, I have a few potentiometers, so I don't have the exact values for this at the moment. Anyway, all the values in the circuit might suffer some modifications. I haven't really built this thing yet, so once I build it and I see how it works, maybe there will be some fine-tuning needed. And finally, I have this daughter board connector, which will be a 9-pin connector that has 2 rows of 9 pins, so 18 pins in total. And this is what I'll be using to connect my effect boards to my main motherboard. So basically, to get an effect built, I will only have to build this part a single time, and then the actual effect will come on a small little board that is connected to this thing. And next time I'll actually start building it to see if it really works. But for now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.